Oh, okay.
No. Okay, so yeah, so I'm just going to kind of read through this. It's kind of basic. So it says linear algebra provides a way of compactly representing, and move this down, and operating on sets of linear equations. So you have some linear equations here, and then you can sort of write them in the compact form A x equals b, and where x is now your variables x1, x2, and a comes from the two equations. So the first row of A is this equation, or I guess the first row of this matrix equation is this first equation 1, and then the second row is this second equation 2. And so that's just a compact way of writing it. A is in the real number matrix set, and by D denotes a matrix with n rows and D columns where the elements belong to real numbers. And then you can write the same thing as a vector with just one dimension. So there's a vector with D real entries. And so it's a matrix with one row, basically, and D columns. Okay, and so I guess here he kind of extrapolates it into like, into sort of more useful machine learning terms. So like these x's can be thought of as dimensions or features or attributes or variables of the problem that you're looking at.
Wait.
Okay.
What can be defined as features? The x.
So
vector?
The individual entries of x. Yeah. So for example, I don't have an example. It's gonna take too long to think about. But yeah, I guess if you think of it as like variables, if you have like, yeah, if you're like trying to fit something, right? And if you're trying to fit a line or some curve, and these x's represent like, yeah, these x's represent like coefficients of that fit, or something like that. It's kind of the idea.
Okay.
Okay. And then some other things we could do with matrices. So we can transpose the matrix, and that's by, so you do that by flipping the rows and the columns. So if you have A that has dimension n by D, this transpose is going to have dimension, the transpose is written like this, A with a T here, and it has dimensions D by n. And then basically for each element of the matrix, the transpose can be written as just the, so if for the original matrix, if J represents the row entry and I represents the column entry, then when you flip it, the row entry is now going to be in the, or the column entry is now going to be in the rows, and the row entries are going to be in the columns. So you just flip them. So I guess, for example, A1, 2, if this first row is now this first column. And then you have some properties of transposes. That's the transpose of a transpose is the original matrix. The transpose of a product, you flip the product and you take the transpose of each element. The sum of two matrices transposed is each matrix transposed. The sum of each matrix transposed individually. And then for square matrices, so if you have a square matrix, you can say it's symmetric. So this idea of symmetry is if you have that A is equal to its transpose. So that means that you basically have a matrix where it's symmetric about its diagonal entries. So x1, x2, blah, blah, blah. And then this down here, we'll call this D. This is also D. So it's symmetric about its diagonal entries. And then it's called anti-symmetric, which was a new thing that I read for me this week. If A is equal to the I guess the polar opposites of its transpose. So negative times, or -1 times the transpose of A. Okay, and so then you can write every single matrix, every single square matrix, every single matrix, sorry, has a sum of symmetric and anti-symmetric matrices. So if you have some matrix A, you can break that up into its symmetric part and its anti-symmetric part. And the way that looks is that you take you take half times A plus A transpose plus half times A minus A transpose. And so if you just like do the math here, you can see that this part and this part will drop out, and then you'll just be left with A.
Oh, I see. Okay, and then I guess this is important because I guess we're saying even for matrices that don't have symmetric properties, we can break it up such that it does.
Mm-hmm.
Okay.
Yeah, and then I think like each of these parts are symmetric. So, or like, I guess this part here, this A plus A transpose, is symmetric. And so you can, if you need to do, I'm forgetting, or I don't really know a situation where this is like applicable per se, but the big thing here is like if you take the sum of a matrix plus its transpose, it's going to be symmetric. And same thing with the other one. So it's going to be anti-symmetric if you take the matrix minus its transpose.
Okay. I think this might be useful because I think there's some linear algebra operations that only work for symmetric matrices. Does that
yeah.
Okay.
Or like there's some properties of symmetric matrices that are useful in some operations, I guess. Yeah.
Okay, I see.
So here he's kind of just showing that G is indeed symmetric and H is indeed anti-symmetric. And so G is this, or G is this, sorry. And then if you take the transpose of G, then using the properties of symmetric of transpose,
Mm-hmm.
then you can separate the sum transpose of A plus A transpose, and that's equal to, yeah. So you can see the same thing with the anti-symmetric.
Epic.
Okay. Okay, and then, okay, so that's it for the basics. And then we'll talk about norms. So norms are basically a way to like informally measure the length of a vector, like the distance that it has. So there's sort of a more formal definition of norms in that it has to satisfy these 4 properties. So I guess let me give an example first before moving on to like the 2 norm of a matrix is X transpose, or of a vector, sorry, times X, which is the sum of, I guess the square root of that, which is the sum of each of the components of, yeah, I guess I'll do this, yeah, for all I square root. So it's basically like multiplying each of X by itself. So X squared, basically, each of the elements in X.
Oh, I see.
So that's an example of the 2 norm.
Okay, I see how that mathematically works. I'm just trying to understand why we're using the word length.
Yeah. I would actually use the word magnitude instead. Length, magnitude. The sort of, what do we use norms for? Yeah, so we can use norms to basically basically maximize and minimize things, right? So if we can calculate how sort of the magnitude of this vector, then we can, I don't know if there's some parts of the slide that does that, but if we can calculate the magnitude of this vector, for instance, and we use this in linear, is it not linear regression, but linear, I guess linear regression or fitting. So if you had some data, B, some vector B that had some data, and then you had some matrix A that had, let's say, okay, let me just do something here. So you have A that, let's say, you're trying to fit some polynomial function or something like that.
Mm-hmm.
And you have some data B from something that you collect, B1, B2, and then you have some X, right, which is the coefficients that how this data is going to correlate, right? So then if you want to find the closest fit, then you would find X that, so the minimum X
Mm-hmm.
that minimizes this function, right? And so this norm is allowing us to basically identify the magnitude of this difference between AX and B, and we want to minimize that magnitude.
Okay, that was a really good example. Thank you.
Yeah.
Now I get it, because I'm like, wow. So it's basically, it's an informal way to say, given all these numbers in this bucket, we can say that its value relative to another bucket can be compared using norm, essentially.
Yeah.
That makes sense?
Yeah. Yeah.
Okay.
That's very true.
Let's see. Thank you.
Yeah. Yeah, and so formally, you can define a lot of different kinds of norms, and they just have to satisfy these 4 properties. So you'll see a lot of different kinds of norms out there. But the properties are, for all X, f of X has to be greater than 0. So the norm of X has to be greater than or equal to 0. So it can't be negative. So it has to have a positive magnitude. The norm of X is equal to 0 if and only if the vector X is actually also 0. So zeros in all the entries. And then for X so for X that's a vector, if you have some scalar T, the norm of the scalar times X is equal to the magnitude of the scalar times the norm of X.
Interesting.
And then for 2 vectors, X and Y, the norm of X plus Y has to be less than or equal to the norm of X plus the norm of Y. So this is a triangle inequality type thing. So it's if you had X and Y, I guess it's the norm of X and norm of Y. Then this plus this.
Mm-hmm.
Yeah, so this is X plus Y, I guess. So yeah, I think you kind of get the picture. So I won't spell it out, but that's kind of the idea here. And then there's some common norms. So L2 norm is probably the most common. So this is kind of your Euclidean distance norm. So you basically just take the sum of all the x's squared, and you take the square root of them. So you can also write this as, a lot of people will just write it as the 2 norms squared, which is equal to, which you can just get rid of the square root basically, and write this as the xi squared. And there's the L1 norm, which is you just take the absolute value of each element in X and you add them together. So it's absolute value. L infinity norm, which is you just take the maximum value inside, like whichever component has the maximum value, that is your L infinity norm. Okay.
Could you actually go back up? I'm sorry.
Yeah, no problem. All the way up?
Back to the L2.
Okay. Can you see it?
Yeah, that's what you wrote before, right? Where you had X transpose.
Yeah. Up here,
well,
yeah.
Except this is, okay, let me try this again. So here you have the L2. Is this the L2 norm where you're writing what you wrote below the definition of norm, or is that different from the L2 norm?
This is the same.
Okay, but the one below has a x2 squared. So would we take
the
L2's number? Yeah, I don't see the difference there.
Wait, say that again?
So at the top, the equation you wrote, where you were given the example, you wrote square root of x transpose times x. And then you simplified that to a summation of xi times xi and the square root of that sum. And if you go to the bottom, there's the L2 norm, which we have the square root of the summation of xi squared, which is basically what you wrote up there. And then you said that that's equal to x2.
Yeah, well, I guess it's not equal, but I'm saying that another way that people will do this is if they don't want to deal with this square root, this is equivalent. This is equivalent because you just get rid of the square root and you just square the norm. Yeah, so because the values are squared and yeah, so they're not equal, but because the values are squared, if you're like minimizing and maximizing something, it'll always give you like those two bounds. Yeah, so you don't need to take the square root per se.
I see. So you can just keep your norm squared term and use that.
Yeah.
Okay, thank you.
Yeah, but they're equivalent, so you can do either one.
Okay. Okay.
And then there's the L1 norm, which is just sum up all the absolute values.
I see.
And then the L infinity norm, which is you just take the maximum absolute value of all the X components.
Okay, and I guess the reason we have different norms is because there's lots of different ways to compare matrices.
Right. So like, yeah, like for example, yeah, let's say like you had some problem where you actually have some like constraint that you just can't, how do I, yeah, I guess you have some constraint that you can't like pass. Like let's say you have a, let's say you're driving a car around the track or something, and you want to basically like bound how far it goes. I don't know a good example of this, but basically there's some bound that you just can't pass at all. And then in your optimization problem, you can now use this L infinity norm to say, okay, just make sure that the norm of this vector that I'm computing is never passing this maximum value or never getting under this maximum value.
Okay.
Or this minimum value, yeah. I guess this is just for the max, yeah. Okay, and then there's just generally this class of LP norms, which kind of can be written as like the L2 norm, and that's where you just take the sum of the absolute value raised to p, and then after you take the sum, you do 1 over p, and so you can check that for the L2 norm and the L1 norm that this works to get the values that are given for L2 and L1. And then you can also check for all these three norms that they do satisfy all these four sort of norm definitions. And then we have like these matrix norms, and the most commonly used one is the Frobenius norm, and it's basically just going to be the trace of A transpose A. So these are just sort of defined, not arbitrarily, but these are defined and they're used for like certain things. But this is like the sort of the most common way to get the magnitude of a matrix is the Frobenius norm is one kind of way to do this. But yeah, I don't know if it's super important right now. And same thing here, if you just square it, then you don't have to take square root. So if you just say AF squared, then you get rid of square root. Okay, so I won't go through this because we kind of already talked about this and it's kind of simple. Let's see, okay, then special matrices. So we have the identity matrix, which is I square matrix with ones on the diagonal and zeros everywhere. A diagonal matrix is a matrix where all the non-diagonal elements are 0. And so this is typically denoted as D, diag, and then you have the elements that are in the diagonal. Two vectors, x and y, are orthogonal if x times y, or the inner product or the dot product, whatever you want to call this, is equal to 0. And so, yeah, so that's the orthogonal definition for vectors in RD. And then if you have a matrix that has RD by D, that is called orthogonal if its columns are orthogonal to each other and are normalized. So every single column, if you just take each column as a vector and multiply any column by another column, the product will be 0. The inner product will be 0 for that matrix. And then you also have the additional, I think this is actually called orthonormal. Maybe this is a typo. So I think it's called orthonormal if the columns are orthogonal and are normalized. Could be wrong about that though, let me see. Oh, okay, okay. Yeah, I'm wrong. So it is called orthogonal if all the columns are orthogonal and normalized, but each of those columns are then called, oh, I hate this, are then called orthonormal columns to each other. So this is not right. So orthogonal matrix has orthogonal and normalized columns. Okay, and then from that property of orthogonality and orthonormality, you'll see that if you take the transpose of a matrix times itself, you'll get the identity matrix. Whereas we know that, I guess it's not mentioned here, but we also know that like if you took the definition of the inverse is that if you took the inverse of a matrix times itself, you would get the identity matrix. So this this orthonormal or these orthogonal matrices are equal to their inverses. So for orthogonal matrix, U transpose is equal to U inverse. And then when you take the inner product of an orthogonal matrix times a vector, or not the inner product, sorry, the norm, the 2 norm of a orthogonal matrix times its times a vector, you'll get the vector back out. And the reason is because of basically from this point here, is that you're basically going to end up, if you write this out as we did, so if we had that, yeah, let me just do it actually. So like that x is equal to x transpose, let's just square it. So I don't have to write the square root. X transpose x, then u x is equal to u x transpose times u x, which is equal to x transpose u transpose u times x, which is equal to x transpose times x, because u transpose u is the identity matrix.
Okay, thanks for writing that out. I need a moment to catch up, if that's okay.
Okay.
No, so you do a lot of linear algebra, correct, for your work?
Yeah, I do.
Okay. How
So
much reading was this?
I read through the handout. I think it was 26 pages, so it maybe took, but it wasn't like, it was pretty big text, so maybe took like a total of, I didn't read it all in one sitting, but maybe across the week it took an hour and a half to read it. Okay. But I already like kind of have taken like classes on a lot of stuff, and a lot of my research stuff uses this. So.
So whenever we're using the U matrix, we're referring to that as an orthogonal matrix typically.
I don't know if it's universally known like that. I think it would be explicit if it's an orthogonal matrix. Someone will say like for orthogonal matrix U or something like that.
Okay.
But in this case, we're just yeah, using U as an orthogonal matrix.
Okay. And then the identity where we show that U, the norm, the L2 norm of UX is just equal to the norm of X, of the L2 norm of X. Why is that useful? Do you know?
I'm trying to think of an example.
I mean, I'm sure there's probably examples later in the slides. I'm just
actually there aren't. I kind of read through it earlier, so there wasn't really. I guess one case is for proofs. So if you can prove that, if you're trying to, for some. So yeah, so this isn't very practical, but like I'm thinking like if you are like writing a paper or something and you want to prove that the norm of like some matrix times some vector is going to be equal to the norm of just a vector, then you can, if you can some way prove that that matrix is orthogonal, then you can use this property. Yeah, so a lot of these are actually like super useful for proofs, and sometimes not that useful practically. But I guess proofs are practical, so I don't know.
Oof. All right.
It's practical if you're trying to write a paper, man.
Yeah.
Okay. So I guess like what I'll say about this is that like if you end up doing, and it sounds like you're going into a space where matrix, like putting things in matrices will be pretty useful. then a lot of these things will just start to pop up, and you'll like do some Googling and you'll remember some of these properties, but it's good to like know kind of, I guess, where they come from.
Yeah.
Okay, so multiplication. So we know the product of two matrices A and B is given by C, where the I and J components is given by basically, so I being the rows and J being columns. So the, yeah, I guess I'm not going to go into detail on this. You could probably already know how to do matrix multiplication. So it's given by this. And then you know that the inner dimensions have to match for you to be able to do multiplication. And then the dot product, which we kind of talked about earlier, is just X transpose times Y. So you take, so X and Y being like sort of the column vectors, you take transpose of X and you multiply by Y and just do matrix multiplication there. And then you can do something called so that's the inner product. And then you can do something called the outer product, where now you take the transpose of the thing that's on the right side. So Y, and this is going to give you a square matrix instead, or not a square matrix, a D by N matrix. If they're the same size, then it's going to give you a square matrix, but a D by N matrix. So basically, so instead of that, you'll have, instead of this X transpose Y, you'll have X 2, 3, and Y like this. Y 1, 2, 3. And you can see just from the dimensions of these, this is a 1 by 3. And this is a wait, what? No, 3 by 1. This is a 3 by 1. Okay. And this is a 1 by 3. And so that'll give you a 3 by 3 matrix here. So that's the outer product. Inner product, outer product. Inner product will give you a scalar. Field number. Okay.
1 sec. But
okay.
Okay.
All right. Okay, so this is just showing that, I think, again. Yeah, just doing the multiplication. And then, so geometrically, like the geometric interpretation for these dot products or inner products are the magnitude. So the dot product is equal to the magnitude of the product of X and Y, product of the magnitudes of X and Y multiplied by the cosine of the angle in between them. So this is what leads to the use of dot products for testing orthogonality. So remember that we talked about like that when a vector is orthogonal, or vectors are orthogonal to each other, the dot product is equal to 0.
Oh, yeah.
So you can see that like if X is here and Y is here, then the theta between them is 90.
Yep.
And cosine of 90 is 0.
Okay.
Yeah, so that's also useful for Euclidean norm of vectors, and scalar projection. So basically the two norm of vectors. It's basically just doing this. It's just dot products, right? So whenever you see Euclidean norm, 2 norm, L2 norm, all the same thing.
Got it.
And then in terms of like scalar projections, you can kind of always think of inner product as a measure of like the correlation between two vectors scaled by the norms of the vectors. So for example, if we just take that these vectors have norm 1, let's just act like they have a unit norm, then you can kind of think of the inner product as like basically projecting this u down to to v, and then multiplying by, it's kind of confusing. Let me think of a better way to explain that. Okay. Okay, so a measure of correlation. So I think maybe a better way to explain it is you can imagine that if u was actually right on top of v, the correlation is like maximized. It's like the same, basically the same vector. And so as you move away from v, then the correlation then sort of becomes like this projection of u onto v. So it's like how much of u can I project onto v? So as you keep going this way, you eventually get here where you can't project u at all onto v, right? When it's 90 degrees away from v. And so, yeah, I guess you can, just from a geometric standpoint, you can think of it like that, as like how much of one vector can I project onto the other vector? And so these could be, you know, this v doesn't have to be here. It could be like this. But you're still kind of mapping the same thing, trying to project one onto the other. Okay. So in this case, u dot v is greater than 0. So it's if you think of it as like both of them being 1, it's 1 when they're both right on top of each other, and it's always sort of less than 1 until you get to the 90-degree point.
Yeah.
And then when you move past that, then the dot product is now negative, because you can project onto the same sort of the same plane, not plane, the same axis that v is on, but you're never quite on v. So you have like a negative projection in a sense.
Quick question. So for inner products, I see we have v dot u. We don't get a different answer if we switch the order, do we?
No, it should be the same. Yeah. Good question. And then here's it being 0 when there's no correlation, basically.
Okay.
Okay. Matrix inversion. Okay, so something that's really important for matrix inversion is this idea of linear independence, and also rank. And so a set of vectors x1 through xd, so each individual vectors, are said to be linearly independent if no vector can be represented as a linear combination of the remaining vectors. So if I had like, for example, if I have, let's just say x1 through xd, and let's say I can represent x2 equal to 5x1 plus 3xd, whatever. So some combination. It doesn't have to use all of them, but some, and then so that it would just be 0 for the rest of them, right? So as long as you can represent at least one of these, vectors with some scalars and some combination of the other vectors, you can no longer call the set of vectors linearly independent vectors. Okay, so we say that the vectors are linearly dependent if you can represent them with some linear combination of the other numbers, of the other vectors. Okay, and so then that leads to the idea of rank. And so column rank is when we're looking at the vectors along the columns of a matrix A. So this is A, these are the columns 1, 2, 3, 4, for instance. So the column rank of a matrix A is the size of the largest subset of columns of A that constitute a linearly independent set. So if I took all these 4 columns as vectors and I tried to represent them, like column 1, for example, with 2, 3, and 4, and I couldn't do that, then, and I did that for all of them, then they're all linearly independent. And I would say that the column rank of this matrix was 4. But if, for example, I can represent 4 by 1, 2, and 3, then they're not all linearly independent, and I can only say that the column rank of this is 3. Of this matrix is 3. So basically, yeah, so the largest subset of columns of A that are going to be linearly independent. And then similarly, you can do the same thing for row rank, where you then take the rows as your vectors instead and try to represent each one with the others, each one vector with the other 3 vectors. Okay. So for example, so for this matrix A, and so we should note that row rank will always be equal to, is that right? Yeah, I think so. Row rank is always equal to column rank. For square matrix.
That's not true.
That's not true?
No, that's only if they're full rank.
Okay.
They're separate.
Okay. Disregard that. Okay, so we have this. So yeah, what are the ranks of the following matrices? So for example, like you can represent 3, 6 by just scaling 1, 2 by 3, and you can represent 2, 4 by scaling 1, 2 by 2. So the only thing that's really, there's only one sort of, you can only take one of these vectors as a linearly independent set, and that would just be taking like 1, 2, for example. So the rank is only 1. Whereas here, I guess they're looking at. Are you sure that's not true, Kevin? For square matrices, the column rank is equal to the row rank.
Let me check.
Okay. Yeah, I mean, I could be wrong, but I feel like. Okay, so anyway, so same thing here. You can kind of go through and check that none of these matrices, none of these vectors can be represented. So this is a linearly independent set. So none of these vectors can be represented as as a linear combination of the other two. And so this is a 4 rank with 3. Well, let me just think about it. So if I have like something like this, 0, 1, 2, and then let's say I wanted to do 2, 4, 6. So for the row rank, oh yeah, I think you're right. Because the row rank of this would be 3, right?
Yeah.
Whereas the column rank is 2. So 2. Yeah, I think you're right, Kevin, actually.
It seems
Yeah.
like column rank is probably a little more common than row rank. Does it really not matter?
Yeah, I do think column rank is more common, but I don't think it matters actually. Column rank is usually when people say rank, you usually think about column rank. I guess the reason why I said that they were equal is because most times people would just say rank. And I guess it's kind of unclear what people mean by just rank if they're not equal. But it might be that column rank is what we generally mean by rank. Yeah, I think that's a safe assumption. If people just say rank, you can assume column ranked. Okay. That's taking a lot longer than I thought it would. Let's see. Okay, so we talked about this earlier. So the inverse of a square matrix is denoted A with a -1. And so it's the unique matrix such that A inverse times A is equal to the identity matrix, and same thing if you multiply the inverse on the right side. Okay, so for some square matrices, the inverse may not exist, and we say that A is singular or non-invertible if the matrix does not exist, and the inverse does not exist, and so in order for A to have an inverse, it must be 4 rank, i.e., all the vectors in it are linearly independent. Okay, and it must be square. So it must be square and must have 4 rank to be invertible. For non-square matrices, we can't take an inverse, so we can just take what's called a pseudo inverse, which is denoted by this A and the plus sign. Sometimes you'll see like a dagger instead. I guess I can't really draw a dagger, but something looks like that instead of like more like a cross than a plus sign. But anyway, and so this is given by A transpose A inverse times A transpose. And let's see, there's some math here. I'm not sure what he's doing here, but there's some ways to derive this. I don't know if that's necessarily useful currently, but like for instance, so the use case of this is like if you had like more data, let's say you're trying to fit that function again, and you have more rows than columns or something, right? So like let's say you had okay, yeah, let me not go deeply into it. But let's say you have like more rows than columns of this matrix, and you want to then figure out the sort of like least squares approximation of this thing. So when you try to minimize this norm, the solution to this problem, and I think this will come up in one of our future lectures, the solution to this problem will be that X is equal to A transpose A inverse times A transpose times B. And so this is the pseudo inverse. So that's mainly the way it's used. So if you had an n by n matrix, you could just say X is equal to A inverse times B, but you can't do that if you don't have a square matrix. So it's useful when you have more data than variables. So n is like your number of variables in X, and m is like the amount of data you collected, because this is also an M matrix or M vector.
Yeah, I think I see. It's almost, we're basically, I don't think overfit is the right word. Maybe it is. But like we're forcing the dimensionality into the end, even though
yeah, you're trying to fit it to n dimensions, but you have like m pieces of data.
Yeah. Okay.
Yeah. And m sort of different models that you're trying to fit. Okay, so trace and determinants. So trace of a matrix is the sum of the diagonal elements in the matrix. And so it has some properties as well. So for a square matrix, A of D by D, the trace of A is equal to the trace of its transpose. And so you can kind of think of that by knowing that if you have any square matrix, like the diagonal elements aren't going to change if you take the transpose. It's going to stay the same. And then for trace A and B, the sum, or the trace of the sum of the matrices is equal to the trace of A plus trace of B. And then for another square matrix, if you have some scalar times the matrix, trace of that is going to be equal to trace of the matrix times the scalar. And then this is really interesting. So for some matrices, ACB, such that ABC, such that ABC is a square matrix, the trace of ABC is equal to the trace of BCA is equal to the trace of CAB. So this is called I think some people call this the cyclic property. And note that you can't just like reorder these in random orientations. They kind of have to be in this, and I don't really know why, but they kind of have to be in, like if you move A over here, you can't then just like swap B and C. So like here we've basically moved A to this side, and you still have B and C multiplied by each other. And same thing here, like we have AB, but we've like moved effectively C to this side, and so it's CAB. So it's not equal to like trace of let's say BAC, for instance. So just something to keep in mind for that.
Can you remind me, a square matrix is one that, I mean, it has the same length rows and columns. Is that all?
That's all, yeah.
Okay.
And then the trace of a matrix helps us easily compute norms and eigenvalues of matrices, as we'll see later. Yeah, so this is for later. And then, yeah, I guess I didn't talk about determinant here, but yeah, I guess we'll talk about it here. So determinant, there's a formula here for how to calculate a determinant of any matrix. And so here for matrix A, it's equal to the sum of the elements of A, ij, times the determinant of a matrix without the row I and column j. So like, I don't know if you recall, if you have some matrix A and you're trying to compute determinants, so you'll do say A, B, C, D. So it has to be a square matrix, first of all. H. Okay, maybe I overkill here. E, F, G, H, I, J. So if we're like going to use this formula to compute a determinant, we basically, if we're at I and J, so let's say we're at 1 and 1, we're going to take, so let's just do it. Let me just write it down. Is equal to -1. So 1, 1 will be times 2. And then A of ij would be A times the determinant of the matrix that doesn't include row I and row j. So that would be F, G, I, J. And then you do that for like basically all the different rows and columns, or all the different columns, J. Yeah, I mean, so you just, I mean, you'll have MATLAB and so you can compute determinants easily, but yeah, so for a 2 by 2 matrix, it's just going to be AD minus BC, and you can check to see that works. If you consider the this MIJ in this case, if you're like here at 1, 1, then MIJ would just be D, and so on. So okay, so properties of determinant. Determinant of a matrix equal to determinant of its transpose. The determinant of a matrix product is equal to the product of the determinants of the two matrices. The determinant is equal to 0 if and only if A is not invertible or singular, or, yeah, let me write this down, or singular, which is another word for it, or the columns are linearly dependent, or not full rank. So all kind of the same terminology. So if A is invertible, then the inverse, or the determinant of the inverse, is equal to 1 over A. And so I really liked the, if I can remember correctly, from the reading this week, I really liked the geometric definition of the determinant as like basically the area that the matrix that the vectors in the matrix like span. So like for like a 2 by 2, you would have like some vector, and these vectors are coming from A. So 1, 2, 3, 4, for example. And so the area is like something like this, that like they span. And then for like a 3 by 3, you have like some like hyper parallelogram that like they're like spanning. I don't even know how to draw it, but but it's like a volume. Yeah, I can't draw it, but it's like some volume that they're like that they can like sort of move in.
I think that makes a lot of sense.
Yeah. Okay, eigenvalues and eigenvectors. So given a square matrix A, we say that lambda, which can be complex valued, is an eigenvalue of A and X, or is an eigenvalue of A, and X, which can be a complex valued vector, is an eigenvector if this equation holds for X not equal to 0. So basically what this equation says is that upon multiplying the matrix A with a vector X, we get the same vector, but scaled by some parameter lambda. So basically, geometrically, I think this is going to be helpful. We're transforming the matrix A from its orthonormal basis to a new set of orthonormal bases X with magnitudes as lambda. So if we think of A as representing some basis with vectors like this, and so this is like A1, A2, let's say it's 2 by 2, and you have some vector X. What's basically happening is we're like basically scaling both, or like what is this? Not scaling, but transforming transforming the matrix from its basis now into this sort of like smaller dimensional basis that is that then is like scaled by some lambda. So let me have a different color maybe. So this is what like A gets turned into. Just like your lambda X.
Okay, one sec. Okay, so I think this probably makes, I mean, sadly we can't really draw in 3 dimensions easily, but I guess when you have a lot of dimensions, eigenvectors are useful because it compresses your information into 1 dimension.
Okay. Yeah. And then computing them is done, yeah, basically like this. So to kind of show that this works, you can like sort of subtract this lambda X from both sides, and then you get something that looks like this, equals 0. And you know that X is not equal to 0, because that's part of the definition of the eigenvalues here. And so you have to have that this is in the null space. Okay, well, don't worry about null space. That this times X basically is going to be equal to 0. And the only way that this times X is equal to 0 is if it's singular. And that means it's not invertible. And let me think of how to explain that better, because I kind of also struggle with. Yeah, well, does that make sense? Because like if I could invert this a minus lambda I, that means that I could write some equation x equal to a minus lambda I times 0, which is 0, which would make x equal to 0. And we already said that x cannot be equal to 0. Oh, sorry, this is inverse. So if I could invert this, then I would have like a minus lambda I inverse times a minus lambda I times x
Oh, I see.
equals a minus lambda I inverse times 0.
Yep. And then
And that would make x equal to 0. And we said x can't be 0.
okay.
So so this equation can only work when this isn't invertible. And like we said from the determinant facts, if something is not invertible, the determinant is equal to 0. And so that allows us to write this equation that the determinant of a minus lambda I is equal to 0.
Okay.
And so then we can do basically just some like determinant computation of this matrix. And so compute the determinant of this in sort of symbolic form. And this will result in a polynomial of degree d as like some lambda d minus 2 lambda d minus 1 dot 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 equals 0. And then you find the roots of that polynomial by equating it to 0. And then the d roots are then the d eigenvalues of A. And they make this, this quantity singular. And then for each of those eigenvalues, you're going to solve this equation equals 0 to find the eigenvector x. So you just basically find the lambdas from this equation and then plug them back in here to this larger equation and solve for each x for each of the eigenvalues.
We did this in ME 161, correct?
Probably, yeah. This is a very common thing because eigenvalues are like super useful. And then here's an example of them doing it. So yeah. Yeah. I don't think I'm gonna go through it, but you can kind of see what they're doing. So basically here is the step of A minus that lambda, and then you find the lambdas. Yeah, I guess, oh wow, okay, they've already given the values here. Okay, so this is them finding eigenvectors. Okay, I see. So they've already found the eigenvalues by doing the first step, and then now they plug that back into the equation, and they plug in the different lambdas. So this is for lambda equals -5, and then they find this eigenvector here. So this is the normalized. I'm assuming this is the normalized eigenvector, which means that the norm of x1 is 1. So you can always normalize by just dividing by the norm of the vector itself. And this is for eigenvalue lambda 2. Same thing here.
I didn't realize that you're going to get different eigenvectors for each eigenvalue.
Yeah, there should be yeah, one eigenvector for each eigenvalue.
Does each
A different one.
Does the number of eigenvalues tell you anything about your matrix?
This is a number? Yes, it does. It tells you things like uh, like linear independence. Yeah, it tells you things about like linear independence and rank and stuff like that. I think we'll talk about it here somewhere. Maybe, maybe not. Yeah, so the number of eigenvalues, the number of like unique, there's a lot of like eigenvalue theory, but the number of unique eigenvalues you have corresponds to the rank of your matrix A. So if like for this thing you have two distinct eigenvalues, and so A you'll know has rank 2.
Got it.
Yeah.
And that's column rank.
Yes. Yeah. Okay. Matrix eigen. Okay, so then you can also write this together. So these individual matrices, in these individual vectors from each of the eigenvalues can be written all together in one big matrix equation as A times X equals X times this big lambda, matrix form lambda, where the columns of X are the eigenvectors that you computed for A, so the eigenvectors of A, and lambda is a diagonal matrix whose elements are the eigenvalues of A. So you basically just take your eigenvalues, you put them in a diagonal matrix, and that's what's going to be in your lambda matrix. And you take your eigenvectors, you put them in the columns of X, and that's what is your eigenvector matrix. And so if the eigenvectors of A are invertible, then you can write this equation. And there are, so this has like some use cases in singular value decomposition, which we'll talk about in a little bit. So I think that's why they sort of bring it up here. So there are several properties of eigenvalues and eigenvectors. Okay, so so this is, now we're kind of getting into the useful part. So the trace of the matrix A is equal to the sum of the eigenvalues that you find of A, eigenvalues of A. So so this is really interesting because you can basically say that, so for your lambda matrix, so it's equal to the trace, I guess, of your lambda matrix.
True.
Yeah. And then the determinant of A is equal to the product of these eigenvalues.
That's why eigenvalues are so special. It's because they just relate to so many other properties.
Yeah. And the rank of A is the number of non-zero eigenvalues of A.
Okay.
So I guess they don't even have to be unique. They just have to be non-zero. And then if A is non-singular, so if A is invertible, then 1 over lambda I are the eigenvalues of the inverse of A.
Okay.
So for instance, if you're trying to find, if you knew that A was invertible, if you can prove that A was invertible, and let's say you're trying to find the trace of A inverse, you can just find the eigenvalues, invert those scalars, which are much easier to invert than a matrix, and then you basically know the trace of your inverse matrix. Okay, and then the eigenvalues of a diagonal matrix. Wait, the eigenvalues of a diagonal matrix. Oh, okay. So if you have a diagonal matrix A, yeah, I guess this is kind of redundant, but the eigenvalues of a diagonal matrix are the diagonal elements of the matrix itself. So if you have a matrix A that is diagonal, so it's diag of A1, A1, A2, AN, then these are also the eigenvalues of A.
Did we talk about why trace is useful? I don't think I remember.
It's kind of a measure also of the length or magnitude of a matrix. So if you remember that the Frobenius norm, I'm not going to scroll all the way up. Let me just write it down here. The Frobenius norm of a matrix squared is equal to the trace of like that matrix.
Okay.
Right. So if you can find the eigenvalues of A trace or A transpose A, and just use that as, so this is also equal to the trace of the eigenvalues of A transpose A.
So once you have that property, now you can determine that that kind of norm easily.
Yeah.
Okay.
Yeah. Okay. And then there's singular value decomposition. So I didn't really know what he was like talking about here. Well, I knew what he was talking about, but I didn't really see. Well, I'll try to tease out what I think was relevant here. So I think here he's talking about like centering, like a centered matrix, and so I think this is useful for like data analysis in a sense. So he defines so this is sigma sigma squared. So this is like your standard deviation. So you have some mean mu, and you have some data that you're sort of going over x, right? And so you're for each x xi, you're computing. So you basically sum over the xi's minus the mean, divide by n, and you get your standard deviation. So then he also defines this centered matrix as a matrix where you subtract all the means from each of the components. So I think it's easiest to think of this in like a data analysis sense. So like when you're working with means and standard deviation and stuff. And so you have some data X that you've collected, and then you can compute the mean. And so you can center the matrix around the mean. And then from a matrix perspective, you can get this X transpose X. I guess this is a vector. Sorry, this is a vector. Not a matrix, vector, but he did write centered matrix. So X transpose X is going to be like your representation of the sigma as well. So this is basically just the same thing. So if you write it out, you'll see that's the same equation as your sigma here. These are equal. And so then you know that the sigma squared is also going to be equal to X transpose, X defined as this, X bar defined as this, transpose times itself divided by n. Yeah. And so for an example of that, he kind of goes into, he makes like some kind of example matrix with some data in it, right? So you have the weights and heights of people in different sections, and you calculate some centered matrix where you're using the mean of the weight, mean of the height, mean of the sections, I guess. And then you can get a covariance matrix by computing this, by computing this x bar transpose times x divided by n. And then if you want to get a correlation matrix, you can do the same thing as you were doing for x. So this is x bar star. But now it has a caveat that you divide it by the standard deviation of like each of these columns.
So go back up actually.
Yeah.
I don't remember what, because I like that he chose an example of grading because we're about to grade. Congrats on finishing.
Oh yeah.
Covariance and correlation. So covariance, I don't think I actually know what that means. Do you know what it means?
So the covariance, I think, is kind of like how it kind of gives you a measure of how correlated, or how I guess that's how I would think about it. How correlated one variable or one data point is to the others, is my understanding of it.
You know what variance is, right, Steve?
So variance, we're trying to get a capture of the spread of the data, right?
Right, and so you can think of that as one variable with respect to itself, but with covariance, you're seeing how one variable spreads with respect to another variable. So like you could have a covariance between, like, let's say it's X, Y, Z, or a weight and height. You might be doing, you might want to see how weight varies with height.
Okay, so you might check the covariance first, and you might say, oh, look, I have pretty low covariance with weight and height. So then you would check the correlation, and this tells you the degree to which it follows the weight. The weight is following the height, for example.
Yeah, pretty much. So like the covariance matrix is going to be, you see how it's 3 by 3? That's because there's 3 dimensions. So so the diagonal of that matrix is just the variance or the standard deviations of different variables, like weight with respect to itself. And then the off diagonals are going to be like weight with height, weight with section, height with section, etc. But the diagonals are just the standard deviations or the variance. I think one is the square of the other.
Okay, I see. That's cool.
So this is like, so would this be like weight height? This would be like weight section.
Yeah, exactly. But it's I think variance is the square. Is it the square or the square root of standard deviation?
I think it is square. Yeah.
Yeah, but that's basically conceptually what it is. And he probably has some equations for that. Maybe.
Yeah, I think he.
Next couple slides.
He might. Yeah. I mean, this is also an equation for it, right? So you can literally compute it from the data. So then in your knowledge, this correlation matrix is then.
I think he's just trying to build up to a future concept called principal component analysis.
Okay.
But it seems like correlation is just the same thing as covariance, except you're centering the matrix first, I think. But I think covariance is definitely the more important concept to understand.
Okay.
Okay, so you can find the covariance for the centered matrix, but the correlation matrix, actually, no, Steve, you can scroll up a little bit. I just want to look at what the centered matrix looks like.
The what? Centered?
Yeah. Oh.
So this one here?
Yeah, I guess so. Where all you do to center it is you change each data point such that it's relative to the mean.
Mm-hmm.
So if correlation is just covariance centered,
I don't think that's true.
I see, but you center it at some point and then you take the covariance. Actually, I'm just confused. Let's keep going. Maybe.
Yeah, it doesn't quite look like it's just covariance centered. It looks like there's some more stuff.
Yeah.
But
so there definitely is some centering going, is what it looks like.
yeah, but I think you're trying to see how much each term, it seems like, because what is this? If you just did this for one measured value, you are essentially computing how many standard deviations, like yeah, isn't that like how close it is? So if you had like 1 minus the mu, right?
Uh-huh.
And then you knew that your standard deviation was something.
Right. Yeah, that's exactly what it is.
If you divide this by the standard deviation, you're asking like how far away are you from the standard deviation, right? Like what fraction of the standard deviation are you?
Oh, so the correlation matrix is actually, it's not like the covariance, which can be the variance for each of the variable onto another variable. This is taking the actual matrix of all my data and it's saying how far, okay.
How many standard deviations away from the mean I am?
Yes.
Yeah.
Okay. So that'll be useful for grading essentially.
Yeah.
Okay. Cool.
So you can see for each student necessarily how far away they are from, how many standard deviations they are away from like the mean.
Oh, this is great. This is going to be some good analysis. We should use our data sets if that's ethical.
So yeah, so I guess this is like, you can use this equation if you want. And so it's just centering the matrix first and then divide down by the standard deviation of that feature.
Okay.
So yeah. And then the last thing, so I think we'll probably stop at the end of these slides because they just took so long. So I don't know, maybe we'll discuss what we'll do. Maybe we're too ambitious in terms of what we're trying to cover each week. But that's an issue because that means we need to, anyway, so we'll figure it out. So signal value decomposition, pretty easy thing to understand. I think it's more of an applicational utility, and it's very useful in a lot of different applications. So you have your sort of X matrix that you have, where N is the number of instances, I guess your measurements that you have, and then D is your dimensions. And in this, it says X is a centered matrix. I don't know if it necessarily has to be a centered matrix, but in this particular case, we're assuming that it's one. And then you have, so you're going to basically decompose it into a unitary matrix times a diagonal matrix times another unitary matrix. And what the unitary matrix means is basically that it's orthogonal and something else. I forget what the other thing is. Might just be that it's orthogonal.
Well, it's orthogonal and it's, what's that word when you can get
square?
Well, it is square, yeah, sure.
I don't know if that's necessarily the case, but it's unitary. But it's orthogonal, and so we know that. Let me look up exactly what unitary means. But yeah, so basically you can represent that matrix X as this, in this form. And sort of like similar to, so then that can help you do a lot of interesting things. So for example, if you're trying to find the covariance matrix that we just discussed up there, and you can break this X down into these different forms, I mean, this singular value decomposition, then you can plug it into that, that computation. And so you'll get something that looks like this when you plug that into X. And then since you know that these are unitary matrices, this is just the identity matrix. And then you're left with these here, V, E squared, and because E is just a diagonal matrix, right? So E transpose E is just going to be E squared. You just take the diagonal components and square them. And then even further, so you can then just divide each of those diagonal components by n, right? Because they're all scalars. It doesn't really affect the matrix. And then what you can do is now you multiply both sides by V, and this becomes the identity matrix here. And so now it looks like an eigenvalue problem where you have the covariance matrix times V, where V is some vector of eigenvectors times equals V times this thing, which basically is a matrix of eigenvectors, a diagonal matrix of eigenvectors. So you can basically kind of write it like this, right? And so now you can see that these values that come from the singular value decomposition, the singular values essentially divided by, the singular values squared divided by n are just the eigenvalues of the covariance matrix. And that is the same as the singular, so I guess not the same, but I guess they're defining the terms here. So lambda I is the eigenvalue of covariance matrix, and sigma I is the singular value of the X matrix. So we can directly calculate eigenvalue of covariance matrix by having the singular value of the matrix X directly. So remember that X was your data point, points, and so you can kind of go through this to calculate the eigenvalues of the covariance matrix, and that will at least give you the variances between each of the components that you're looking at. But then I guess you wouldn't have the, yeah, you will sort of have shrunk it into that one dimension. So you wouldn't have the variance in between each component, but yeah, I'm not sure what the sort of, I guess that is the idea here, is that you can just directly calculate the eigenvalues of the covariance using SVD of X. So there's probably some applicational thing here that that isn't coming through in this one lecture. Maybe it'll come through in later lectures if we just keep it in mind. But
so
yeah,
so defining this EI or sigma I, singular value of X matrix, and we're just going to suspend that in our minds for now and say, like, this is a thing. We're going to see how it's useful later, probably.
Yeah, well, yeah. Well, one way it's immediately useful is that it can help us calculate the covariance matrix.
Okay.
Or it can help us calculate the eigenvalues of the covariance matrix, which we know, since the covariance matrix is always going to be a diagonal matrix, right? You agree with that? Like these are always going to be, is that true? Is a covariance matrix always a diagonal matrix, Kevin? Or symmetric matrix, sorry.
Symmetric.
I think it's always symmetric, right? It's going to have the same rows and columns. Because it's just like...
Yeah, so basically is
You mean square?
No, I mean symmetric.
I don't know what symmetric
Is the variance of W to H the same as the variance of H to W?
Huh.
Oh, yes, I believe so.
Okay. Yeah, I think so too. So since the covariance matrix is always symmetric, I guess you didn't even need it to be though. Yeah, you didn't really need it to be, but by calculating those eigenvalues, you automatically now know this variance of W, variance of H, and variance of S, because these are just the eigenvalues.
Okay, I see.
Yeah, so that's one way it's immediately useful. I'm assuming there are more ways.
And you get the singular value X, or I'm sorry, you get the singular value sigma I just by, if you scroll back up, because it looks like you get that, you pull that out when you do the decomposition. And because like, I guess the assumption decomposing it is really easy. So once you assume that sigma,
In these slides, he doesn't really talk about how to decompose them. He kind of just talks about the application of it, but could you go up one slide? Yeah, so he just says we can decompose a matrix X into three different matrices, two that are unitary, one that's diagonal. But this is pretty much derived from the eigen decomposition. So the singular values are calculated based on the eigenvalues of X, and then U and V, the unitary matrices, are calculated based on the eigenvectors. But he doesn't really go into that here.
Okay, I see.
Yeah.
So I see. So the underlying mechanics behind singular value decomposition is really computing the eigenvectors, eigenvalues, and vectors to produce this.
Yeah.
Okay, that makes sense.
Yeah.
But as far as for us who are more focused on the application, we just need to know once we decompose it, this singular value matrix. Did I see that? Not whatever the sigma part. The sigma matrix is just going to be super useful when I'm computing other stuff.
Mm-hmm.
Okay.
Yeah, and actually, so just from this, we can also compute the covariance matrix fully by V transpose, right?
Yeah.
Yeah. So as long as you start off with like your data, right? Start off with your data matrix X, and then you can just use MATLAB to do the singular value decomposition. And as soon as you get those U, V, and U, V, and sigma, then you can compute the covariance matrix using just V and sigma.
Right, but I bet MATLAB probably also has some covariance function too.
Yeah, probably.
Yeah, it has everything.
Okay, so this is the last thing I think, and then I think we'll have to bounce. But so basically, intuitively, the way you can think of SVD is just as like a change of basis. I think to kind of think of it. So where you have this one, so you have this matrix or I guess vectors. You have these vectors V1 and V2, and if you apply the matrix A to them, it transforms them into this thing, right? So you've scaled this vector by that amount, scaled that vector by that amount, and you've rotated them in some. Yeah, so you've done some transformation, some scaling, and some rotation to the vectors. Versus if you use the singular value decomposition, it's just like taking them to the same place, but first you So you basically just do the steps in different ways. So first, I think this is well, I don't actually know what they're doing, but I think this is like the scaling or the rotation. No, this U is the rotation. So this is something, and then the singular values is the scaling, and then the U is the rotation. I'm not sure what this, or I guess this is like getting them into their X and Y components or something.
Oh,
That's the change of
I don't
basis.
know,
That's rotating the axes.
Okay. Yeah. So, but I think the idea is that it's the same transformation if you apply all three of these matrices versus just the original matrix to the vectors. Okay. And so that's it.
Yeah.
Let me stop recording.